Level 1 Anomaly. Look at the green danger meter at the very bottom. You've just entered Level 1 Anomaly. The inner scale covers a wide range of events, not just major disasters. It captures minor operational failures and safety anomalies. This level is defined by a loss of control rather than a casualty count. At Level 1, your experience is characterized by a deviation from standard operating procedures. The data is straightforward. The radiation released to the public is absolute zero. Nothing dangerous escapes the reinforced concrete walls. Instead, an anomaly is measured by minor failures in defense and depth, which refers to your overlapping safety systems. These anomalies are actually frequent in the industry. Reporting them is considered a sign of a robust safety culture, ensuring small cracks don't become structural failures. A documented example occurred at the Tricastin nuclear power plant in France in 2008. During a routine tank cleaning, operators accidentally spilled about 75 kilograms of untreated uranium solution onto the floor. It was a significant operational error that violated internal protocols. While the safety nets functioned as designed to protect workers, a small amount of the solution leached into the ground, triggering a temporary ban on consuming water from private wells in the immediate vicinity. No one was hurt and the public health impact was negligible, but the breach of containment protocols moved the meter. The external world remains largely unaffected and you leave the shift unharmed. It is a minor operational incident where the systems prevented escalation. Level 2 incident. The danger meter ticks up to a sickly yellow-green. You are now at Level 2. An incident. A significant failure has occurred and there are direct measurable consequences inside your facility. However, radiological barriers remain intact. The measurement remains zero radiation released to the public and the death toll is zero. The surrounding population is unaware of the situation inside. However, the safety status has changed. Level 2 is measured primarily by personal exposure or a significant failure in safety layers. To understand the scale, the legal annual limit for a nuclear worker is typically 20 millisieverts, while the average person receives about 2 to 3 millisieverts per year from natural background radiation. Level 2 is triggered when you receive a radiation dose exceeding 10 millisieverts in a single event. A specific example is the Asco nuclear power plant in Spain in 2008. During maintenance, radioactive dust was accidentally sucked into the ventilation system. Due to a monitoring failure, this dust was released inside the building, contaminating several workers. As you perform routine work, the dosimeter on your chest activates. You've been exposed to a concentrated dose due to significant failures in safety provisions. You are sent to the medical wing for decontamination. While this dose increases long-term cancer risk, it is insufficient to cause acute radiation sickness immediately. Your safety barriers protected the public, but internal protocols failed. Before we escalate to the serious incidents where safety margins disappear, if you are finding this breakdown valuable, please take a second to subscribe and like the video. Level 3, Serious Incident. Level 3 is classified as a serious incident. This level represents a near-miss scenario with a significant reduction in safety margins. While radiation released to the public remains minimal below the threshold for neighborhood evacuations, the on-site situation is critical. Level 3 is characterized by severe contamination resulting in massive worker exposure. We are no longer discussing annual limits. You are now receiving a massive dose, typically around 1 full sever. This is sufficient to cause severe acute health effects, including radiation, burns, and nausea, though usually not immediate death. Your safety systems are under maximum stress. Consider the Vandelos plant in Spain in 1989. A fire broke out in the turbine building, a non-nuclear area, but the fire spread to the cabling systems that powered the reactor's safety functions. This common mode failure destroyed the vital cooling pumps. Without cooling, the reactor faced a potential meltdown purely due to heat buildup. Personnel fought the fire and manually restored safety systems, barely avoiding a catastrophic core failure. While the containment held, the economic and structural damage was terminal. The operator determined that the cost of repairing the fire damage and upgrading the safety systems to meet new standards was too high. The facility was permanently decommissioned. You survived, but the plant is non-operational. Level 4. At Level 4, classified as an accident with local consequences, the physical containment barriers have failed. This level marks the release of radioactive material into the environment and the beginning of lethal consequences. Once containment is breached, the scale shifts from measuring personal exposure to measuring environmental contamination in terabarrels of iodine 131. At level 4, the radiation release equals tens of terabecquerels. A radioactive plume breaches the facility, necessitating local food controls. You are warned that consuming local produce or milk poses a toxicity risk. A critical distinction at this level is that it requires at least one fatality from direct radiation. Refer to the 1999 Tokura accident in Japan. To save time, technicians mixed uranium and stainless steel buckets not designed for nuclear material, violating safety procedures regarding geometry and mass limits. They added excessive material, accidentally initiating a criticality event, a self-sustaining nuclear chain reaction in an open vessel. This triggered a blue flash caused by Cherenkov radiation, which occurs when charged particles move through a medium faster than the speed of light in that medium. While the nuclear fuel itself stayed in the tank, the reaction blasted high-energy neutron beams through the walls of the building. The workers absorbed a lethal dose instantly, suffering massive cellular damage and prolonged fatal radiation sickness. Residents within 350 meters were advised to stay indoors because neutron radiation can penetrate standard structures. It was a localized accident, but the environmental release remained relatively limited. Before we move on, I want to give a quick shout out to my supporters. You guys honestly make videos like this possible. Also, do you want to help decide what the next video is about? Supporting the channel gives you a vote on future topics so you can have your say. There is more information on how you can support in the description below. Level 5, the danger meter shifts to dark red. Level 5 is an accident with wider consequences, marked by severe damage to the reactor core. The radiological release increases exponentially. Level 5 is measured by the release of hundreds to thousands of terabarols of radioactive iodine 131. Containment structures are compromised, necessitating public evacuations. While the death toll from direct radiation may be zero, the societal disruption is extensive. The defining case occurred at 3M Island in 1979. A pilot-operated relief valve in the primary cooling loop stuck open, allowing vital cooling water to escape as steam. However, the indicator light on the control panel showed the valve as closed because it indicated the signal sent to the valve, not the valve's physical position. Due to this ergonomic design failure, operators assumed the system was full of water when it was actually boiling dry. Temperatures in the core reached 4,300 degrees Fahrenheit, causing the fuel rods to melt. This reaction created a massive hydrogen bubble inside the pressure vessel, creating a fear of a secondary explosion that could breach the containment building. The situation required the evacuation of 140,000 residents. The disaster was eventually mitigated by the concrete containment building, which prevented a Level 7 release, but the facility was lost. This event led to a global overhaul of nuclear training focusing on human factors engineering. Level 5 represents a fundamental mechanical and systemic failure. Level 6 serious accident. Level 6 represents a massive uncontained environmental disaster. The measurement increases to tens of thousands of terabarrels. At this stage, emergency countermeasures are required for survival. This level results in long-term contamination of the surrounding region, requiring exclusion zones. While Level 7 events are well known, the Kisham disaster in 1957 serves as a primary example of Level 6. At a secret waste storage facility in the Soviet Union, a cooling system failed in a tank containing highly liquid, radioactive waste. Over time, the water evaporated, leaving behind dried nitrate and acetate salts. These precipitated chemicals acted like dynamite. The tank buried deep underground, eventually overheated and exploded with force equivalent to 70 tons of TNT, blowing the 160-ton concrete lid off the bunker. A radioactive plume known as the East Urals radioactive trace contaminated a populated region of 20,000 kilometers. The primary long-term contaminant was strontium-90, a bone-seeking isotope that replaces calcium in the human body, causing long-term health issues. The event was kept secret for nearly 30 years, leaving residents unaware of the radiological hazard affecting their food and water supply. You are living in a significant environmental disaster surpassed only by the maximum classification on the scale. Level 6 indicates the permanent loss of regional land use. We are about to reveal the absolute worst-case scenario for humanity. If you've learned something new today, hit the hype button now to to help this video reach more people. Level 7, Major Accident. The highest classification on the INES scale. This represents a catastrophic release of snorts, hundreds of thousands or millions of terabarrels. This results in widespread health and environmental effects across multiple countries. There have been 2 Level 7 events in history. The first was Chernobyl in 1986, where a reactor design flaw led to a power excursion and explosion, physically destroying the core and dispersing radioactive material across the continent. The second was Fukushima in 2011, where an earthquake and tsunami disabled backup generators, leading to 3 simultaneous core meltdowns. The classification of Level 7 is largely driven by 2 isotopes, iodine-131 and cesium-137. Iodine-131 has a short half-life of 8 days and targets the thyroid, which is why potassium iodide pills are issued immediately. Cesium-137, however, has a half-life of 30 years and binds to the soil, rendering the land uninhabitable for decades. A notable paradox exists at this level. While the Level 4 accident at Tokura resulted in immediate fatalities from radiation, the Level 7 Fukushima disaster caused 0 immediate deaths from radiation exposure. The ANA scale at Level 7 measures the magnitude of environmental impact rather than immediate casualties. It signifies a geological scale event resulting in contamination that persists for centuries. You are observing a permanent alteration of the environment, a level of destruction that requires generations to remediate.